The mantis does not wait for hunger to sharpen its aim. Long before a fly drifts into lethal range, it rehearses. In the dappled understory of a late summer field, where grasses sway in shallow arcs and leaf tips tremble under faint wind currents, a solitary mantis raises its forelegs and strikes at nothing visible. A shadow passes across a blade of grass, and the mantis lunges. A leaf flickers in peripheral motion, and the forelegs snap shut again. These are not mistakes. They are calibrations. Each movement of vegetation, each ripple of wind, provides shifting reference points against which the mantis measures distance, acceleration, and strike timing. In this quiet shadow boxing, the predator is not wasting energy. It is tuning a weapon system that must operate with uncompromising precision. The raptorial forelegs of the praying mantis are often described as weapons, and they are lethal when required. But biologically, they are more accurately understood as articulated tools engineered for exact placement. Each foreleg is modified into a folding arm equipped with spines arranged along the femur and tibia, like interlocking teeth. When the leg closes, these spines form a cage that traps prey in a fraction of a second. Yet speed alone does not determine success. The mantis must calculate angle, reach, and grip placement with remarkable accuracy. A strike that lands too early catches only air. A strike that lands too late allows prey to veer away. A strike that grips the wrong segment of a struggling insect risks damage to delicate spines or allows escape. The apparent simplicity of the motion masks an extraordinary neuromuscular coordination system refined through millions of years of selection. As the mantis rehearses on wind-driven leaves, its compound eyes remain fixed forward, mounted on a highly mobile triangular head capable of rotating almost a full semicircle. This mobility is not theatrical, it is integral to depth perception. Unlike most insects, mantises possess a form of stereoscopic vision, allowing them to gauge distance by comparing input from both eyes. When a leaf sways toward and away from the mantis, subtle shifts in visual disparity inform the predator about range and motion trajectory. Each mock strike recalibrates the neural circuits that translate visual information into motor output. The mantis is effectively adjusting a biological algorithm. If target speed increases, foreleg acceleration must match. If angle shifts, joint rotation compensates. What appears to be random swiping is, in ecological reality, ongoing maintenance of a precision system. Even failed practice attempts carry evolutionary value. A misjudged lunge teaches the mantis about the outer boundary of its reach. Overextension is costly in the wild. Every unnecessary strike expends energy and briefly destabilizes the mantis posture, potentially exposing it to its own predators, such as birds, reptiles, or larger arthropods. By learning its effective strike radius through rehearsal on harmless stimuli, the mantis reduces the likelihood of wasteful lunges when real prey enters range. In this way, the rehearsal phase acts as a filter, ensuring that genuine attacks are reserved for targets with high probability of capture. The predator refines restraint as much as aggression. The ecosystem surrounding the mantis reinforces the need for such discipline. Insects do not move predictably. A fly may hover, dart sideways, or spiral upward without warning. A grasshopper may launch itself in an explosive jump powered by elastic energy stored in its hind legs. The mantis must integrate these erratic trajectories into split-second decisions. Its forelegs close in less than the blink of a human eye. Yet the decision to initiate that strike requires precise timing. Launch too soon, and the prey's evasive maneuver leaves empty space between spines. Launch too late, and the opportunity disappears entirely. Through repeated rehearsal against environmental motion, the mantis fine-tunes this threshold, balancing patience against reflex. Thermoregulation adds another layer of complexity. As an ectothermic organism, the mantis muscle performance depends on ambient temperature. On cool mornings, foreleg acceleration may be slower, reducing strike effectiveness. During these periods, shadowboxing becomes even more critical. By testing its own responsiveness against moving vegetation, the mantis assesses whether its muscles are primed for successful predation. As the day warms and metabolic rate increases, strike speed improves, and the rehearsal transitions seamlessly into real hunting. The mantis does not conceptualize this shift, but natural selection has shaped behavior that accommodates physiological constraints. Practice becomes a diagnostic tool for internal readiness. Camouflage further complicates the rehearsal environment. The mantis body mimics leaves, twigs, or even flower petals depending on species. This crypsis allows it to remain undetected by both prey and predators. However, camouflage requires stillness. Excessive or poorly timed movement undermines concealment. Through controlled rehearsal strikes directed at non-prey stimuli, the mantis learns to confine motion within acceptable limits. It rehearses without advertising its presence. The forelegs extend and retract with minimal disturbance to surrounding foliage, preserving the illusion that the mantis is simply another fragment of plant matter swaying in the breeze. Predator-prey interactions sharpen this necessity. Birds scanning from above are sensitive to sudden movement. A reckless lunge at an unreachable insect could reveal the mantis' location. By calibrating distance and speed through low-risk practice, the mantis reduces conspicuous failures during genuine hunts. In effect, shadowboxing is an investment in stealth. It refines not only mechanical precision, but also ecological timing, aligning predatory action with the rhythms of the environment. The mantis grip mechanics also benefit from rehearsal. The spines along the forelegs must engage prey exoskeletons at optimal angles to prevent slippage. Different prey types present different textures and structural resistances. A soft-bodied caterpillar compresses under pressure, while a beetle's hardened elytra deflects spines unless gripped at joints. When the mantis snaps at leaves or stems during practice, it inadvertently tests resistance and tactile feedback. Sensory receptors along the legs relay information about contact force and alignment. These micro-adjustments accumulate, enhancing future success when the target struggles violently in its grasp. Ironically, the mantis' stillness, often interpreted as patience, conceals constant neurological activity. Visual neurons track motion across the compound eyes field, distinguishing between random background sway and biologically meaningful movement. Rehearsal refines this discrimination. If every flicker triggered a full attack, energy would be squandered. Instead, the mantis uses minor test strikes to recalibrate its response threshold, ensuring that genuine prey elicits a committed, rapid response while irrelevant motion is ignored. The ecosystem becomes both training ground and testing apparatus. In regions where mantises coexist with other ambush predators, competition intensifies the value of precision. A delayed strike may allow a spider to claim the same prey. Conversely, an overly aggressive lunge may result in entanglement within another predator's web. Practice helps maintain the balance between decisiveness and caution. The mantis must strike only when probability aligns with opportunity. As daylight shifts and insect traffic increases, rehearsal gives way to execution. A fly drifts within calculated range. The mantis's head tilts slightly, triangulating distance through binocular vision. Muscles tense, joints align, and the forelegs snap forward with rehearsed efficiency. The spines interlock around thorax and wing base, immobilizing the prey before it can react. What appears instantaneous is the culmination of countless silent calibrations against wind, shadow, and leaf. In this predator, training is not a separate phase from survival. It is survival's quiet foundation. The mantis shadowboxing, invisible to casual observers, reveals a deeper evolutionary truth. Precision is not improvised. It is practiced in the margins of stillness, refined against harmless motion, and perfected before necessity demands it. The forest understory appears still at first glance, but stability is an illusion shaped by scale. At ground level, between moss stems and scattered leaf litter, movement never truly ceases. Ants trace chemical highways invisible to larger creatures. Midges hover in columns of humid air. Sunlight fractures through canopy gaps, shifting in slow arcs that alter shadow geometry across bark and soil. In this layered, constantly recalibrating world, a jumping spider waits, not in rigid ambush, but in quiet assessment. Its body remains compact and poised, yet the large forward-facing eyes sweep methodically across the terrain. Hunger is not required to trigger this vigilance. For the jumping spider, scanning is continuous practice, a rehearsal woven into daily life. Unlike many spiders that rely primarily on vibration through silk, jumping spiders possess some of the most acute vision among arthropods. Their principal eyes, positioned centrally, deliver high-resolution forward imagery, while secondary eyes provide a wide field of motion detection. Together, they create a sensory system capable of depth perception and precise distance estimation. The spider does not simply detect movement, it evaluates trajectory, scale, and speed. When a gnat crosses the field of view, the spider's cephalothorax pivots, aligning its principal eyes for detailed inspection. The animal pauses, but this pause is computational. Within fractions of a second, it measures the angular disparity between its eyes and calculates the distance to target. Even when the insect drifts out of reach or proves unsuitable as prey, the spider has rehearsed a measurement. The stalking behavior that follows often resembles hesitation to an untrained observer. The spider advances in short, deliberate increments, lifting and placing each leg with care. These micro-approaches serve multiple purposes. They refine the angle of attack, ensuring that the eventual jump will follow a trajectory free of obstacles. They test the stability of the substrate. A loose grain of sand or unstable bark fragment could disrupt takeoff force, altering launch velocity and compromising success. By shifting weight gradually, the spider gathers tactile information through sensitive hairs along its legs. It learns the firmness of the surface before committing to a leap. In this way, each incremental step is both reconnaissance and rehearsal. The jumping spider's leap is powered not by muscular contraction alone, but by hydraulic pressure. By rapidly increasing hemolymph pressure within its legs, the spider extends them explosively, launching its body forward with remarkable acceleration. The physics of this mechanism demand precise alignment. A slight miscalculation in angle or distance translates into missed prey and wasted energy. Therefore, long before a true hunting opportunity presents itself, the spider practices these calculations. It orients toward moving leaves, adjusts position relative to shifting light, and performs partial crouches that appear almost like aborted launches. These motions fine-tune neuromuscular timing and pressure control. The spider rehearses without fully committing. In ecosystems where prey density fluctuates, such continuous training is advantageous. On days when insects are abundant, opportunities for successful capture may be frequent, but during lean periods, failed attempts become costly. Energy reserves in small arthropods are limited. By constantly calibrating visual estimation and launch mechanics even when not starving, the spider maintains readiness. When a suitable prey item enters range, the transition from assessment to attack appears instantaneous. The apparent spontaneity of the pounce conceals thousands of prior micro-adjustments encoded in neural circuits shaped by repetition. Predator-prey interactions reveal further depth to this preparation. Many insects possess their own defensive strategies. Flies initiate rapid escape responses triggered by visual looming stimuli. Leafhoppers leap unpredictably. Ants may counterattack with chemical defenses. The jumping spider must anticipate these reactions. During stalking, it often pauses when prey moves, freezing to avoid detection. These pauses are not passive. The spider is recalculating, factoring in the prey's orientation and potential escape vector. By rehearsing approach sequences on non-prey stimuli, such as drifting debris or other spiders beyond striking distance, it refines its capacity to predict motion patterns. The rehearsal is cognitive as much as mechanical. Thermal conditions influence this precision. As ectotherms, jumping spiders depend on environmental warmth to optimize muscle performance and hydraulic responsiveness. In cooler temperatures, reaction times slow and hemolymph pressure builds less rapidly. During such periods, the spider may engage in extended scanning and low-risk micro-movements rather than full jumps. These subdued rehearsals allow it to gauge its own performance threshold. As sunlight warms the substrate and internal temperatures rise, the spider's readiness increases. Practice adapts fluidly to physiological state. The spider's visual acuity also supports complex spatial memory. Research has demonstrated that some jumping spiders can plan detours to reach prey not directly accessible, indicating a level of cognitive mapping unusual among invertebrates. In the field, this manifests as exploratory movements around stems and rocks, even when no immediate prey is present. These exploratory circuits refine the spider's understanding of three-dimensional structure within its territory. When prey appears in a partially obstructed position, the spider can select an approach path with minimal hesitation. What seems like foresight is the product of repeated spatial rehearsal embedded in daily movement. Camouflage plays a complementary role. Many jumping spiders display patterns that break up their outline against bark or foliage. However, they do not rely solely on concealment. Their hunting strategy balances stealth with active pursuit. During micro-approaches, the spider adjusts body orientation to minimize shadow casting and maintain a narrow profile relative to prey vision. By practicing these alignments against harmless moving targets, it reduces conspicuous errors during genuine hunts. Evolution has favored individuals capable of integrating visual assessment with body positioning at a fine scale. Even interactions with conspecifics provide training opportunities. When two jumping spiders encounter one another, ritualized displays may occur. Raised forelegs and lateral movements communicate intent without immediate combat. These displays demand precise leg control and distance awareness. Though primarily social signals, they reinforce motor patterns relevant to hunting. The boundary between territorial negotiation and predatory rehearsal blurs, revealing how behaviors can serve multiple adaptive functions. In moments when a real target enters optimal range, the culmination of this constant training becomes visible. The spider aligns its body, lowers slightly, and secures a silk dragline behind it as a safety tether. The dragline is not merely insurance against falls. It reflects the spider's integration of risk management into predation. Should the leap fail, the spider can climb back and attempt again. Then the hydraulic surge propels it forward. Contact is precise, legs wrapping around prey before escape reflexes can activate. The event lasts less than a heartbeat, yet its success depends on innumerable rehearsed calculations. Within the intricate fabric of the ecosystem, the jumping spider embodies preparation disguised as patience. Its ceaseless scanning, cautious micro-approaches, and aborted crouches are not indecision, but refinement. The forest floor becomes a training ground where angles are tested, footing evaluated, and trajectories simulated long before necessity compels action. In this predator, mastery arises not from a single decisive leap, but from a lifetime of silent rehearsals performed in plain sight. At the edge of an old oak woodland, where sap bleeds slowly from fissures in bark and the air thickens with the scent of fermentation, male stag beetles gather after dusk. The forest at night is not silent, but layered with restrained movement. Moths drifting toward residual warmth stored in tree trunks, woodlice navigating damp leaf litter, and bats tracing erratic arcs above the canopy. Against the rough vertical surface of a sap-running oak, two armored figures approach one another with deliberate caution. Their bodies are heavy, polished in dark chestnut tones, and crowned with exaggerated mandibles shaped like antlers. These structures, oversized relative to the rest of the head, appear ornamental at first glance, yet they are the focal point of ritualized combat that defines the beetle's reproductive success. The confrontation begins not with immediate violence, but with assessment. Each male orients its body, antennae sampling chemical cues that confirm the rival's species and maturity. The mandibles open slightly, revealing inner teeth designed not for slicing flesh, but for gripping and levering. In many encounters, neither beetle suffers fatal injury. Instead, they engage in a structured grappling sequence that resembles a measured test of physics more than a chaotic brawl. One male hooks his mandibles beneath the thorax of the other and attempts to lift. The opponent braces, tarsi gripping bark with hooked claws adapted for climbing vertical surfaces. Muscles in the prothorax contract, transmitting force through rigid exoskeletal plates. The contest is one of leverage, balance, and timing rather than indiscriminate damage. These ritualized fights function as training as much as competition. The forest canopy offers limited breeding territories rich in sap flows attractive to females. A male that cannot hold position risks being displaced and losing access to mating opportunities. Through repeated grappling with rivals of similar size, a beetle refines its ability to read shifts in center of gravity. When a rival leans forward too far, even slightly, The opposing male can exploit that imbalance, using his mandibles as lifting arms to flip the opponent backward. The goal is often to dislodge rather than maim, sending the rival tumbling from the trunk to the leaf litter below. The fall rarely proves fatal, but it is decisive in the immediate contest. Biomechanically, the mandibles of stag beetles are remarkable. Though imposing in size, they are hollow and relatively lightweight, minimizing energetic cost while maximizing reach. Their curvature allows insertion beneath a rival's body, converting upward force into rotational torque. This torque depends on precise alignment. A poorly angled lift results in wasted effort and potential self-exposure. Through ritualized bouts, males calibrate the angle of insertion and the speed of lift required to overcome resistance. Muscular hypertrophy develops over time. Repeated contests strengthen the thoracic musculature responsible for head and mandible movement. What appears as brute force is, in fact, the outcome of incremental conditioning. Thermal conditions influence these encounters. As ectothermic insects, stag beetles rely on ambient warmth to achieve optimal muscle performance. On cooler evenings, movements are slower, contests prolonged. In warmer conditions, lifts are more explosive and falls more dramatic. By engaging in frequent ritualized fights across varying temperatures, males effectively test their capabilities under different physiological states. This repeated exposure prepares them for unpredictable environmental fluctuations during peak mating season. The ecological stage on which these battles unfold adds further complexity. Sap flows attract not only stag beetles, but also wasps, moths, and other sap-feeding insects. Competition is multidimensional. A distracted male focused solely on a rival risks intrusion by other species. Thus, awareness extends beyond the immediate opponent. Through repeated contests, males refine not only grappling mechanics, but also situational vigilance. Antennae flick periodically, detecting shifts in chemical landscape even as mandibles remain locked. In many cases, fights terminate without catastrophic damage because evolutionary pressures have favored restraint. Mandibles are formidable, but not optimized for piercing exoskeleton. Instead, they are designed to apply controlled pressure. Severe injury would reduce the population of viable males and destabilize breeding opportunities. Ritualization channels aggression into predictable sequences, minimizing lethal outcomes while still establishing hierarchy. This balance between intensity and limitation exemplifies how natural selection can sculpt behavior toward efficiency rather than excess. Repeated grappling also enhances timing. When two males interlock mandibles, each feels the micro-movements of the other through tactile feedback transmitted along rigid cuticle. A slight tremor in resistance may signal fatigue or an attempt to shift grip. Experienced individuals respond instantly, adjusting leverage before the rival can recover balance. These adjustments are not conscious strategies, but reflexive patterns strengthened by repetition. Training occurs through survival of successful responses. Interestingly, smaller males sometimes adopt alternative tactics, avoiding direct confrontation and attempting to mate opportunistically when larger rivals are engaged. Even in these interactions, ritualized fighting among dominant males indirectly trains the entire population. The presence of active contests shapes spacing, vigilance, and territorial boundaries within the sap-rich microhabitat. The arena becomes a dynamic network of force and counterforce. Predation risk further reinforces the importance of efficient combat. Nocturnal predators such as owls and small mammals patrol the forest floor. A beetle thrown from the trunk may survive the fall, but becomes vulnerable during recovery. Therefore, the stakes of each lift extend beyond pride. Controlled contests reduce prolonged entanglement that might attract attention. Swift resolution benefits both victor and loser in minimizing exposure time. The physical architecture of the beetle supports these behaviors. The exoskeleton acts as both armor and lever system, distributing mechanical stress across sclerotized plates. The neck region, though appearing slender, is reinforced internally to withstand torsional forces generated during lifting. Through repeated practice bouts, structural resilience is tested but rarely exceeded. Failures in alignment are corrected in subsequent encounters, reinforcing motor pathways that favor successful leverage. As mating season progresses, these ritualized contests intensify in frequency. A male that has engaged in numerous practice bouts exhibits smoother, more decisive lifts. His timing improves, energy expenditure decreases, and balance adjustments become nearly instantaneous. When confronted by a rival in a high-stakes scenario where a sap flow supports multiple receptive females, his experience manifests as efficiency. The rival may be overturned within seconds, ejected from the vertical arena before prolonged struggle can ensue. In the quiet after a contest, the victor repositions himself near the sap wound, mandibles partially raised in readiness. The fallen beetle climbs again, often to re-engage. This cyclical pattern transforms the oak trunk into a training ground shaped by evolutionary design. Strength, leverage comprehension, and reaction speed are honed through repetition. Catastrophic damage is rare, but the lessons are permanent within the constraints of an insect lifespan. In this woodland theater, the stag beetle's ritualized fight is more than spectacle. It is preparation embedded within competition, an adaptive system that balances aggression with sustainability. Each grapple refines the physics of lifting and the art of balance reading. When the decisive battle arrives, the outcome appears immediate, yet it rests upon countless controlled encounters that preceded it. The forest, indifferent yet precise, has shaped a combat style where training and survival are inseparable. In the humid darkness of a tropical forest, where tree trunks sweat resin and the air hangs heavy with fermentation, a rhinoceros beetle climbs with deliberate force. The bark beneath him is uneven and damp, layered with algae, and the residue of sap flows that attract a congregation of night feeders. Moths press close to the sticky surface, their wings powdering the air with fine scales. Smaller beetles cluster along fissures, feeding in brief, cautious intervals. Above them all, the rhinoceros beetle ascends like a moving fragment of armor, his curved horn projecting forward from his head as though it were an extension of the tree itself. The horn appears theatrical, an extravagant ornament exaggerated by evolution. Yet its true function is mechanical, precise, and rooted in the physics of leverage. The encounter begins not with a charge, but with contact. Another male approaches along the same trunk, drawn by the same sap resource and the same reproductive opportunity. Their antennae unfold, lamellate segments fanning outward to sample chemical signatures in the air. Recognition occurs through scent and proximity. Neither male attempts to pierce or slash. Instead, they align their bodies face to face, horns nearly touching. What follows resembles a test of structure rather than a chaotic clash. Each beetle lowers his head, attempting to wedge the upward curve of his horn beneath the thorax of the other. The goal is not to wound, but to lift. This horn wrestling is a form of powerlifting disguised as combat. The rhinoceros beetle's body is built around this action. Massive thoracic muscles anchor to reinforced internal ridges of the exoskeleton, converting contraction into upward torque. The horn acts as a lever arm, amplifying force generated at the base of the head. Yet the lift succeeds only if the feet are anchored. The tarsi grip bark through hooked claws that penetrate crevices and irregularities in the surface. Before exerting force, each beetle braces, adjusting stance to maximize friction. These micro-adjustments are subtle but critical. A misplaced foot reduces stability, transforming strength into wasted motion. Many bouts unfold as extended grapples in which neither male immediately dominates. They push and strain, horns sliding against cuticle, testing resistance. The forest floor below waits as a silent consequence. A successful lift sends the rival tumbling from the trunk, often several body lengths downward. The fall rarely kills, but it removes the displaced male from immediate access to sap and mating territory. The vertical arena of the tree becomes both stage and measuring device, where gravity enforces hierarchy. Through repeated duels, the rhinoceros beetle develops not only muscle mass, but also refined coordination between horn angle and body alignment. A horn inserted too high fails to gain purchase, too low, and it glances off the opponent's abdomen. Over time, individuals that engage frequently in these sparring rounds learn the precise angle required to slide beneath a rival's center of mass. The thorax must brace at the moment of lift, transferring force without compromising balance. These contests build proprioceptive awareness, the insect's sense of its own body position relative to the substrate and opponent. The horn is not a stabbing weapon, but a calibrated lever whose efficiency depends on practiced timing. Thermoregulation influences the outcome of these duels. As ectotherms, rhinoceros beetles rely on ambient heat to optimize muscle contraction speed and strength. In cooler conditions, lifts are slower, struggles prolonged. As nocturnal temperatures stabilize in tropical climates, muscle performance reaches peak efficiency. Engaging in repeated bouts across fluctuating temperatures effectively conditions the beetle's neuromuscular system to operate under varying constraints. The sparring functions as both contest and conditioning, strengthening the exact muscle groups required for decisive flips. The ecological context intensifies the importance of such preparation. Sap flows are ephemeral resources, appearing when bark is damaged and vanishing as wounds dry. Males that secure prime positions near active flows gain increased access to females attracted by nutrient-rich sap. The competition is immediate and physical. However, outright lethal aggression would be counterproductive to population stability. Evolution has favored a ritualized structure in which strength and leverage determine dominance without routine fatal injury. The horn's design reflects this balance. Its smooth curvature and absence of sharp cutting edges indicate selection for lifting rather than piercing. Predator presence adds urgency to these interactions. Tree-climbing mammals, nocturnal birds and reptiles patrol the forest canopy. Prolonged chaotic fighting would attract attention. The ritualized nature of horn wrestling promotes swift resolution. A rapid lift and drop limits noise and movement. The loser, though displaced, often survives to compete again. Each defeat becomes additional training, refining foot placement and horn insertion in future encounters. Interestingly, horn size varies among males, influenced by larval nutrition. Individuals that developed in nutrient-rich environments grow larger horns and more robust thoracic musculature. Yet horn size alone does not guarantee victory. Technique matters. Smaller males sometimes win against slightly larger opponents by achieving superior leverage. Repeated sparring teaches the reading of subtle cues, the shift of weight before a rival attempts a lift, the angle of horn alignment that signals imminent upward force. Anticipation becomes as valuable as raw strength. The mechanics of lifting reveal deeper evolutionary ingenuity. When the horn slides beneath the rival's body, the beetle's neck joint absorbs significant stress. Internal reinforcement within the head capsule distributes this stress across sclerotized plates. The exoskeleton functions as both armor and framework, channeling mechanical energy efficiently. Through sparring, structural resilience is tested repeatedly, ensuring that only individuals with robust architecture persist in dominant roles. The vertical nature of the arena shapes behavior further. Gravity assists the victor, but punishes imbalance. Anchoring feet against bark requires sensitivity to microtextures. The beetle's claws detect slight irregularities, and leg muscles adjust pressure accordingly. During prolonged grapples, both males continuously recalibrate stance to prevent slipping. This constant feedback loop between tactile input and muscular output resembles athletic training more than lethal combat. As the night deepens and humidity rises, the pace of encounters increases. Sap scent intensifies, drawing additional rivals. A seasoned male that has engaged in numerous bouts moves with practiced economy. He positions himself strategically, conserving energy until a challenger approaches. When contact occurs, the lift is decisive, honed through repetition. The rival is levered upward and cast from the trunk in a controlled arc. The victor remains anchored, horn raised slightly, maintaining dominance without pursuing further aggression. In this humid forest theater, the rhinoceros beetle's duel is a form of biomechanical rehearsal embedded within reproductive competition. Each contest builds the precise combination of anchoring strength, thoracic bracing, and horn leverage required for success. The bouts resemble sparring rounds in a gymnasium carved from bark and resin, where force is measured, technique refined, and dominance asserted without habitual destruction. Survival does not demand indiscriminate killing. It demands mastery of lift, balance, and timing. The rhinoceros beetle's power is not accidental spectacle. It is engineered through repetition, sculpted by environmental constraints, and sustained by the physics of leverage. When the decisive moment arrives, the flip appears effortless. Yet beneath that moment lies a history of controlled contests, each one strengthening muscle fibers and refining coordination. The forest offers no applause, only the silent confirmation that training disguised as duel has secured another night of dominance on the vertical arena. By late afternoon, the air above the meadow begins to stratify, warm layers rising from sunlit grasses, while cooler currents slip down from shaded hedgerows. In that invisible architecture of temperature and turbulence, a wasp traces a looping path that appears almost decorative at first glance. The movement is neither random nor urgent. It is a patrol, an aerial circuit repeated with slight variations in height and radius. Below, a paper nest clings to the underside of a wooden beam, its hexagonal cells exposed like the open face of a living machine. The wasp's flight intersects this landmark repeatedly, banking sharply before accelerating into open space, then curving back again. The sequence resembles rehearsal more than pursuit. The wasp's body is engineered for these drills. A narrow waist separates thorax from abdomen, increasing flexibility during tight turns. The thorax houses powerful indirect flight muscles that deform the exoskeleton to drive wing beats at high frequency. Each acceleration depends on precise coordination between wing angle and stroke amplitude. During patrol loops, the wasp modulates these variables continuously, testing lift against crosswinds and adjusting for subtle gusts generated by heated ground. The environment is not static. Rising thermals can tilt a trajectory unexpectedly. By flying repeated circuits, the wasp calibrates its response to these shifting forces, refining neuromuscular timing long before genuine conflict demands it. Males, particularly during mating season, intensify these aerial exercises. They establish loose territories around landmarks such as nest sites, flowering shrubs, or patches of exposed soil. When another male enters this airspace, pursuit begins. Yet these chases are often brief and ritualized rather than lethal. The resident male accelerates toward the intruder in a straight high-speed dart, wings producing a faint vibration audible at close range. The intruder veers, sometimes circling back to test resolve. What follows is a sequence of feints and mirrored turns, each wasp matching the other's movement. The engagement ends not with injury, but with separation, one male retreating beyond the informal boundary. Such controlled confrontations function as flight training embedded within social structure. Reaction speed improves through repetition. The wasp learns to anticipate angular shifts in a rival's path, adjusting wing beat asymmetry to pivot mid-air. These corrections occur within fractions of a second, yet they are not improvised. Each prior chase has reinforced neural pathways linking visual input to motor output. Compound eyes track motion across a wide field, while ocelli on the top of the head detect changes in light intensity that signal orientation relative to the horizon. Together, these sensory systems stabilize flight during rapid maneuvers. The threat display that sometimes precedes pursuit is equally instructive. A male may hover briefly, abdomen lowered, legs extended, wings raised slightly in a posture that exaggerates body size. This display conserves energy compared to full combat while testing the rival's willingness to escalate. If the intruder hesitates, the resident male has asserted dominance without collision. If the intruder persists, the transition to chase is immediate. Through repeated displays, the wasp refines posture and timing, learning how subtle variations in wing angle or body tilt influence perception. The violence remains measured, a rehearsal of escalation rather than indiscriminate attack. Environmental context shapes these drills. Near the nest, workers engage in foraging flights that demand navigational precision. They memorize landmarks, calibrating return paths through visual mapping of surrounding vegetation. Males patrolling the same airspace intersect with these routes, adjusting their loops to avoid interference. This constant traffic requires fine control to prevent mid-air collisions. Rehearsal chases inadvertently sharpen this coordination. A wasp that can track and pursue a rival without losing orientation relative to the nest demonstrates mastery over complex spatial geometry. Thermoregulation influences aerial performance. As ectotherms, wasps depend on ambient temperature to maintain muscle efficiency. Early in the morning, before the sun has warmed the thorax, flight is slower and less agile. Patrol loops during these cooler hours are lower and more conservative. As temperature rises, wing beat amplitude increases, enabling rapid acceleration. Repeated drills across the day expose the wasp to varying thermal conditions, effectively conditioning muscles to operate near their physiological limits. By the time a genuine territorial dispute occurs during peak warmth, the body has already adapted to maximal output. Predator presence adds further dimension to these exercises. Birds such as bee-eaters and flycatchers patrol open airspace, scanning for erratic flight that signals vulnerability. A wasp, engaged in chaotic, uncontrolled combat, would attract attention. Ritualized aerial displays limit unpredictability, keeping maneuvers within practiced bounds. Rapid darts are short, feints controlled. The choreography reduces exposure time and avoids prolonged spirals that could betray location. Thus, what appears as sparring also functions as predator avoidance training. The aerodynamic structure of wasp wings supports these rapid transitions. Transparent membranes reinforced by veins distribute stress evenly during acceleration. During high-speed chases, wings flex slightly, absorbing turbulence while maintaining lift. Repeated aerial drills test these structures without subjecting them to catastrophic strain. Microfractures in wing veins could compromise survival, so natural selection has favored controlled conflict over destructive collision. The wasp learns the limits of its own architecture through repetition. Occasionally, two males collide lightly, legs tangling briefly before separation. Even these contacts are instructive. Tactile feedback during mid-air grappling informs balance adjustments. The wasp senses the weight and resistance of the rival, recalibrating center of mass instantly. Such brief entanglements rarely result in injury, yet they contribute to the refinement of motor control under stress. As evening approaches and the meadow cools, patrol loops tighten. The wasp passes close to the nest entrance, antennae sampling pheromonal cues that confirm colony integrity. The repeated circuits have mapped the thermal currents and wind patterns of this territory. When a genuine intruder appears, perhaps a rival male intent on mating or a predatory insect drawn to the nest, the response is swift. The wasp accelerates along a trajectory rehearsed countless times, closing distance with controlled precision. Threat posture transitions seamlessly into pursuit, and pursuit into decisive displacement. In this aerial domain, violence is seldom reckless. It is structured, rehearsed, and contained within boundaries that favor survival over destruction. Patrol loops, sudden accelerations, and feints form a continuous training regimen embedded in daily life. The wasp's body, tuned by repetition, responds automatically when true confrontation demands it. What appears spontaneous to the observer is in fact the culmination of hundreds of prior circuits traced through warm air above grass and wood. The meadow does not record these drills, yet they shape the dynamics of territory and reproduction. Through controlled aerial contests, reaction speed sharpens, flight control stabilizes, and dominance hierarchies form without habitual lethality. The wasp's rehearsal of aggression ensures that when genuine threat emerges, the sequence of posture, dart, and chase unfolds with practiced efficiency. The air itself becomes a training ground, sculpting a predator whose mastery lies not in chaos, but in disciplined motion. At the threshold of a honeybee hive, the air never truly settles. Even on calm days, currents ripple outward from the entrance as hundreds of wings beat in overlapping rhythms. The opening itself is modest, a narrow portal cut into wax architecture and reinforced by propolis, yet it functions as the primary checkpoint between the colony's interior and the volatile world outside. Foragers arrive heavy with nectar or dusted in pollen, their flight paths direct and purposeful. But interspersed among them are individuals that do not carry resources. They stand at the lip of the entrance, facing outward, antennae raised and forelegs braced. These are guard bees, and their behavior resembles constant rehearsal more than intermittent reaction. The guard's posture is deliberate. Abdomen angled slightly downward, mandibles ready but not yet open, antennae sweeping in controlled arcs. Each arriving bee is intercepted. antennae touch, tracing along the cuticle of the newcomer in rapid pulses. This inspection is not casual greeting, but chemical verification. Honeybees recognize nestmates through cuticular hydrocarbons, a colony-specific blend shaped by shared diet and environmental exposure. When a returning forager approaches, her scent profile aligns with the colony's signature, and she is admitted with minimal delay. When a foreign bee arrives, perhaps from a neighboring colony seeking to rob stored honey, the chemical mismatch triggers escalation. The inspection process itself functions as training. Guard bees do not encounter threats only during emergencies. Instead, they repeatedly sample variations in scent, recalibrating their recognition thresholds. The colony's odor changes subtly with seasonal forage, temperature shifts, and internal microbial activity. Guards that constantly practice inspection maintain sensitivity to these evolving signatures. Over time, the colony as a whole becomes more accurate at distinguishing ally from intruder. This refinement is not centrally directed. It emerges from countless interactions at the entrance. When suspicion intensifies, posture shifts. A guard may raise her abdomen, exposing the sting apparatus and releasing a trace of alarm pheromone. The chemical signal, primarily composed of isoamyl acetate, disperses rapidly, alerting nearby workers to potential threat. Yet the response is graded. Not every mismatch results in immediate stinging. Often the guard will push the suspect bee, using head and forelegs to dislodge her from the entrance. These controlled confrontations resemble drills more than full combat. The intruder may retreat without injury, while the guards return to inspection stance. Through repetition, they refine timing, learning how much force to apply before escalation becomes necessary. Environmental context shapes these rehearsals. During nectar dearth, when floral resources are scarce, robbery attempts increase. Neighboring colonies probe each other's defenses, seeking access to stored honey. Guard bees experience more frequent challenges during such periods, effectively increasing the intensity of their training. The colony adapts. Guards become quicker to detect subtle scent discrepancies and faster to mobilize reinforcements. Conversely, during abundant bloom, defensive thresholds may relax slightly, conserving energy for foraging. The entrance becomes a dynamic training ground responsive to ecological pressure. Thermoregulation intersects with defense. Honeybee colonies maintain internal brood temperature within a narrow range, despite external fluctuations. Workers fan their wings to cool overheated interiors, or cluster tightly to generate warmth during cold spells. Guard bees positioned at the entrance are exposed to ambient conditions more than interior workers. Their readiness depends on muscle temperature. On cooler mornings, inspection may proceed more slowly, with reduced aggression. As the day warms and thoracic muscles reach optimal performance, reaction speed increases. Continuous inspection under varying thermal conditions ensures that guards remain physiologically prepared when a genuine predator approaches. Predator encounters test this preparedness. Wasps, particularly during late summer, hover near hive entrances, attempting to snatch returning foragers. The guard's training in rapid inspection and coordinated response becomes critical. When a wasp approaches, alarm pheromone spreads through the entrance cluster, triggering a collective surge. Multiple workers launch simultaneously, targeting wings and legs of the intruder. The choreography appears instantaneous, yet it reflects countless prior minor skirmishes and inspections. Each rehearsal at the threshold has sharpened response sequences embedded in neural circuits. Interestingly, not all defense involves immediate stinging. In some cases, guards form a barrier by clustering tightly at the entrance, reducing the opening's effective size. This physical blockade is a coordinated maneuver requiring spatial awareness and communication through touch and pheromone exchange. Repeated minor disturbances at the entrance train bees to assemble quickly into such formations. The hive thus functions as a self-organizing security team, refining procedures without centralized command. Within the colony, age-related division of labor contributes to this process. Younger workers typically perform interior tasks, such as brood care before transitioning to foraging and eventually guarding roles. By the time a bee becomes a guard, she has accumulated experience navigating the hive's interior and exterior landscapes. Her sensory system has been exposed to a range of odors and social interactions. Guard duty becomes the culmination of earlier stages, integrating chemical recognition with motor coordination honed during flight. The sting itself represents a costly last resort. For a honeybee, deploying the sting against a vertebrate predator results in fatal injury as the barbed lancets remain embedded in elastic skin. Against other insects, however, the sting can be withdrawn and reused. Guard bees therefore calibrate their aggression depending on the nature of the threat. Through repeated inspections and minor confrontations, they refine discrimination between intruders that require lethal response and those that can be repelled through pushing and biting alone. The violence remains controlled until escalation becomes unavoidable. Alarm pheromone release also functions as rehearsal. Small releases during minor disturbances prime nearby workers, increasing sensitivity without triggering full attack. This graded signaling allows the colony to practice coordination. The scent dissipates quickly, leaving no lasting damage but reinforcing communication pathways. Over time, the colony's collective reaction speed improves. What appears to be spontaneous swarm defense is in fact the product of daily drills at the entrance. The hive interior reflects the outcome of this vigilance. Brood cells remain protected, honey stores preserved, and queens safe from intrusion. The constant inspection at the threshold is not merely defensive reflex, but adaptive refinement. Each antennal tap, each push against a stranger, and each measured alarm release contributes to a learning system distributed across thousands of individuals. As evening approaches and foraging traffic declines, guard bees remain at their posts. The air cools and the hum softens, yet inspection continues. Even in relative calm, minor scent variations and stray insects prompt brief checks. The colony never fully suspends training. In this living fortress, security is not a static barrier, but a behavior continuously rehearsed. The honeybee hive, then, is not only a center of nectar processing and brood rearing. It is a dynamic training facility where defense protocols are refined through repetition. Guard bees practice inspection and graded aggression daily, transforming potential violence into structured procedure. When a real threat emerges, the response feels immediate because the sequence has been enacted countless times before. The entrance becomes both boundary and classroom, shaping a colony whose survival depends on collective rehearsal as much as on individual courage. Before sunrise fully dissolves the mist above the rainforest floor, the first lines are already in motion. From a wide, cratered nest entrance shaped like a collapsed funnel in the soil, columns of leafcutter ants pour outward in disciplined streams. Each worker carries nothing at first, moving with empty mandibles and antennae constantly sampling the ground ahead. Within minutes, the outbound lane thickens into a living road that arcs toward the canopy, where soft, new leaves await harvest. The return lane soon forms alongside it, ants marching back with fragments of foliage held aloft like bright green sails. The traffic appears choreographed, yet no single ant directs the flow. The system trains itself through repetition. The trail is not merely a path worn into soil, but a chemical corridor reinforced continuously by pheromones. As workers walk, they deposit scent markers from glands at the tip of the abdomen, creating a gradient that guides nestmates along efficient routes. When an ant deviates slightly around a stone or root, she lays a parallel chemical trace. If the detour proves shorter or smoother, subsequent ants reinforce it, gradually shifting the main highway. Minor missteps and collisions are not errors in isolation, they are feedback mechanisms. Through thousands of micro-corrections, the colony refines the geometry of its transportation network. Traffic density plays a critical role in this refinement. When outbound and inbound lanes intersect, brief antennal contacts occur. Each ant pauses for a fraction of a second, adjusting angle and speed to avoid obstruction. These interactions resemble drills in lane discipline. The more frequently they occur, the more efficiently ants navigate around one another. Studies have shown that heavy traffic can actually increase flow efficiency in leafcutter ants because repeated encounters reduce hesitation. Workers learn, at a distributed level, how to maintain spacing and minimize bottlenecks. The colony as a whole adapts to its own congestion. The physical environment continuously challenges this system. Rain reshapes the forest floor, washing away pheromone trails and depositing debris. Fallen twigs force rerouting. Predators, such as ant-eating birds and parasitic flies, patrol above the columns. Each disruption requires rapid recalibration. Workers encountering an obstacle begin exploratory loops, laying new scent traces until a stable bypass emerges. The repeated construction and abandonment of paths function as collective rehearsal. The colony becomes adept at redesigning infrastructure under pressure. At the leaf source, training continues. Workers ascend shrubs and trees, selecting leaves not for immediate consumption, but as substrate for fungal cultivation within the nest. The true food of leafcutter ants is a symbiotic fungus grown on processed plant material. Each leaf fragment must be cut, transported, and prepared to support fungal growth. Young workers learn cutting technique through trial and error, adjusting mandible placement to maximize efficiency. Older workers perform these actions with minimal waste. The repetition of harvesting reinforces muscle coordination and decision-making at a scale where individual improvement translates directly into colony success. Inside the nest, the harvested leaves are processed into a pulp and inoculated with fungal hyphae. The fungus digests plant cellulose, producing nutrient-rich structures consumed by the ants. This symbiotic agriculture depends on precise environmental control. Workers regulate humidity and temperature within subterranean chambers by adjusting tunnel openings and relocating brood. Thermoregulation here is communal. Through constant minor adjustments, the colony maintains conditions optimal for fungal growth. Practice is embedded in maintenance. Repeated corrections ensure stability even when external temperatures fluctuate. Defense training unfolds along the trails and at the nest entrance. Leafcutter colonies attract predators ranging from vertebrates to parasitic insects that lay eggs on workers. Soldiers, distinguished by enlarged heads and powerful mandibles, patrol alongside smaller workers. When a disturbance occurs, such as a vibration in the soil or sudden shadow overhead, alarm pheromones are released. Nearby ants respond by freezing momentarily, then clustering toward the source. Minor disturbances often end without escalation, but each alarm event reinforces reaction speed and coordination. Soldiers engage in controlled biting during such drills. When a non-threatening object brushes the trail, a few workers may latch briefly before releasing. These short engagements calibrate bite force and grip duration. Against real intruders, such as rival ant species attempting to raid fungal chambers, the response becomes sustained and coordinated. Workers swarm the attacker, biting in unison, while soldiers anchor themselves with mandibles locked. The choreography reflects countless minor rehearsals triggered by routine disturbances. Interestingly, the presence of parasitic phorid flies introduces another layer of training. These flies attempt to lay eggs on the bodies of workers carrying leaf fragments. In response, smaller hitchhiker ants sometimes ride atop leaf pieces, scanning for incoming flies. When a fly approaches, the hitchhiker lunges, deterring the parasite. This behavior emerges from repeated exposure. Workers refine vigilance through constant scanning, integrating visual and tactile cues into defensive reflexes. The colony's migration behavior also reveals systemic training. When fungal gardens are compromised by disease or environmental stress, leafcutter ants relocate entire operations. Trails to new sites are established through exploratory forays, pheromone reinforcement, and gradual shift of traffic. The same principles governing daily leaf transport apply at larger scale. Minor collisions and corrections during migration reinforce efficient route formation. What appears to be spontaneous mass movement is in fact a culmination of habitual trail-building practice. Predator encounters underscore the value of this training. An anteater probing the soil with a long snout disrupts tunnel entrances, forcing immediate defensive clustering. Workers swarm exposed areas, biting and spraying formic acid in coordinated bursts. The speed of assembly reflects constant rehearsal. The colony does not deliberate. It responds through ingrained patterns shaped by daily minor alarms. Within this living infrastructure, no ant perceives the full architecture. Yet through local interactions, global order emerges. Each antennal touch, each brief collision on the trail, refines the system. Over time, routes straighten, traffic smooths, and defense responses synchronize more rapidly. The colony trains as a distributed organism. its intelligence expressed through patterns rather than centralized command. As dusk settles and outbound traffic diminishes, returning ants still adjust spacing along narrowing lanes. Even reduced flow serves as reinforcement. The system never fully resets. It accumulates adjustments across days and seasons. Rain may erase chemical trails, but the colony rebuilds them with improved efficiency, informed by prior configurations. The leafcutter ant colony embodies preparation at scale. Individuals practice cutting, carrying, and biting, but the greater lesson unfolds in traffic flow and coordinated defense. Minor collisions become instructional moments. Alarm responses sharpen through repetition. The rainforest floor, etched with temporary chemical highways, functions as a training ground for collective survival. When true crisis strikes, whether predator or rival colony, the response appears seamless, because the system has rehearsed its own efficiency thousands of times in the quiet rhythm of daily work. At first light, when humidity still clings to the understory and dew beads along every exposed filament, the web appears as architecture suspended between trees. Threads stretch across open air in a nearly perfect orb, anchored to branches, vines, and sometimes human structures that intrude into forest margins. Each strand glows faintly gold as sunlight filters through canopy leaves. At the center, legs extended in precise symmetry, waits the golden silk orb-weaver. The web is not a permanent monument. It is a daily reconstruction, a living instrument tuned and retuned against gravity, wind, and the weight of potential prey. During the night, damage accumulates. A moth's desperate thrashing tears spiral lines. A falling twig snaps a radial support. Even minor fluctuations in temperature alter tension within the silk as humidity influences elasticity. By dawn, the spider often consumes portions of the damaged web, recycling protein to conserve resources. Then the rebuilding begins. The spider releases a single dragline, allowing air currents to carry it until it catches on a distant support. This initial bridge thread becomes the foundation for the frame. The process resembles engineering rehearsal. Each anchor point is tested through gentle tugs before additional lines are attached. If a branch flexes excessively under tension, the spider abandons that anchor and selects another. Silk production is energetically expensive. Specialized abdominal glands secrete different silk types, each with distinct mechanical properties. The frame and radial threads consist of strong, relatively non-sticky silk capable of bearing load. The capture spiral, laid last, contains adhesive droplets that increase prey retention. As the spider moves in widening circles, attaching each spiral segment with meticulous spacing, she calibrates distance between threads. Spacing too wide allows smaller insects to slip through. Too narrow increases silk cost and reduces structural efficiency. Through repeated daily construction, the spider refines this balance, adjusting spacing based on recent prey availability and environmental wear. Tension control is equally critical. A web under excessive tension may snap under sudden impact, while insufficient tension dampens vibration signals. The orb-weaver tests radial lines by plucking them gently with her legs, sensing oscillations transmitted through mechanoreceptors. These receptors, located primarily on leg joints, detect minute changes in frequency and amplitude. By adjusting attachment points and tightening or loosening threads, the spider tunes the web much like a musician tuning strings. Each rebuild serves as practice in interpreting vibrational feedback. Environmental context complicates this calibration. In open clearings, wind exposure increases, demanding stronger anchor lines and slightly altered geometry to distribute stress. In denser foliage, airflow diminishes, allowing finer capture spirals optimized for smaller insects. The spider learns from prior failures. A web destroyed by wind the previous afternoon prompts stronger frame construction the next morning. A series of successful captures of large beetles may encourage wider spacing to conserve silk without sacrificing efficiency. Each iteration embeds environmental memory into architecture. Predator interactions also shape this engineering workout. Birds sometimes blunder into webs, tearing entire structures in seconds. Larger insects, such as dragonflies, can break through capture spirals if impact force exceeds silk strength. The spider's response is rarely panic. She retreats to a safe perch, then returns to assess damage. Through repeated reconstruction, she develops a nuanced understanding of which structural elements fail first and how to reinforce them. Over time, anchor points become strategically placed along sturdier branches, and radial lines are oriented to better absorb directional wind stress. The golden coloration of the silk itself may serve multiple purposes, including camouflage in sunlit environments and attraction of certain insect prey that perceive ultraviolet cues. Regardless of its ecological advantages, the hue also reflects silk protein composition and alignment. During rebuilding, the spider modulates extrusion speed and tension to maintain consistent filament diameter. Minor variations alter mechanical performance. By repeating these adjustments daily, the spider maintains silk quality under varying humidity and temperature. Thermoregulation indirectly influences web performance. As an ectothermic predator, the orb-weaver's activity depends on ambient warmth. Early morning construction occurs at moderate temperatures that allow controlled movement without rapid desiccation. During hotter midday conditions, silk may become more pliable, affecting tension. The spider's practice in rebuilding under different thermal states enhances her ability to predict silk behavior. She learns, through tactile feedback, how environmental heat alters elasticity and adjusts accordingly. When prey strikes the web, the true test of calibration begins. A small fly produces high-frequency, low-amplitude vibrations distinct from the heavy oscillations of a beetle. The spider interprets these signals through legs extended along radial threads. Experience accumulated through construction improves discrimination. By understanding baseline tension and geometry intimately, the spider detects anomalies quickly. A well-tuned web transmits clearer signals, allowing faster localization of prey. The act of wrapping captured insects further refines silk control. The spider immobilizes prey by rapidly rotating and swathing it in non-sticky silk. Even this behavior benefits from daily construction practice. The muscles coordinating spinneret movement and leg placement are conditioned by repeated web building. Precision in spiral spacing translates into precision in wrapping. Occasionally, the spider dismantles an entire web, even without catastrophic damage. This may occur when prey density declines or environmental conditions shift unfavorably. The decision to rebuild is adaptive recalibration. Each new web reflects lessons from the previous structure, adjusting geometry and tension in response to changing circumstances. The forest becomes both workshop and testing ground. Symbiotic interactions add further complexity. Small kleptoparasitic spiders sometimes inhabit the orb, stealing captured prey fragments. The orb-weaver tolerates low levels of theft, but may adjust web design to minimize access, thickening certain radial lines or altering hub placement. These modifications are incremental and informed by experience. Through daily engineering, the spider balances cost and benefit within a shifting ecological network. As dusk approaches, the web shimmers in fading light, nearly invisible except where dew clings. The spider rests at the hub, legs attuned to the web's language. The structure is not static, but a dynamic extension of her sensory system. Every anchor point, every spiral spacing, embodies a day's worth of testing and correction. When a moth collides violently, the web absorbs impact as calibrated, tension distributing across radial lines. The spider moves with confidence because the instrument beneath her has been tuned through repetition. In the life of the golden silk orb-weaver, engineering is not a singular act, but a daily discipline. Rebuilding and recalibrating transform silk into both trap and teacher. Each web teaches what holds and what fails, refining structural intuition and vibrational interpretation. The forest air, heavy with moisture and movement, provides endless variables. Through constant reconstruction, the spider evolves within her lifetime, honing an architecture that is simultaneously habitat, hunting device, and training apparatus. By mid-morning, the wetland has begun to shimmer. Sunlight strikes the surface of the pond in fractured reflections, and the air above the water warms into a layered column of rising thermals. Reed stems sway gently at their tips, while their bases remain still, rooted in dark sediment rich with insect larvae and decaying plant matter. Within this vertical landscape of heat and movement, a scarlet dragonfly traces a deliberate arc along the shoreline. His body is a narrow lance of red suspended between four transparent wings, each beating independently in a rhythm that allows forward thrust, hovering stability, and sudden reversal. The patrol appears relaxed, almost ornamental, yet it is neither idle nor purely territorial. Every loop is rehearsal. The dragonfly does not wait for prey to demand precision. He trains in open air long before a mosquito crosses his path. A straight glide transitions into a sharp, banked turn, followed by a rapid acceleration that briefly outpaces the breeze. Then he decelerates into a hover above a patch of emergent vegetation. These maneuvers are not random flourishes. They maintain muscle tone and recalibrate reflexes within a constantly shifting aerial environment. As an ectotherm, his flight performance depends on thoracic temperature. Early in the morning, he basks with wings angled to absorb solar radiation, elevating internal heat to power indirect flight muscles. Once warmed, the patrol begins, reinforcing neuromuscular pathways through repetition. The dragonfly's visual system shapes this training. Large compound eyes dominate the head, composed of thousands of ommatidia that together create nearly panoramic vision. The upper regions are specialized for detecting prey silhouetted against bright sky, while lower regions resolve contrast against darker water surfaces. During patrol loops, the dragonfly continually samples these visual fields, adjusting flight path in response to subtle motion cues. Even when no prey is present, he performs interception-like maneuvers, accelerating toward drifting debris or adjusting trajectory around invisible wind currents. Each action refines the timing between visual detection and wing beat modulation. Interception is the dragonfly's defining predatory strategy. Unlike ambush hunters that wait, dragonflies calculate the future position of moving prey and align their flight to meet it. This requires predicting trajectory based on speed and direction. Through constant patrolling, the dragonfly rehearses these calculations without committing to capture. He may surge forward, then veer aside at the last moment, as though practicing the geometry of pursuit. These aborted accelerations maintain reaction speed while conserving energy. Territorial boundaries provide structured routes for such drills. A male scarlet dragonfly often defends a stretch of shoreline where females lay eggs among aquatic plants. He memorizes landmarks, a bent reed, a floating leaf cluster, a dark patch of submerged vegetation. Patrol circuits follow these features in repeated sequences. When another male intrudes, aerial contests unfold, marked by mirrored loops and sudden climbs. Yet these chases rarely escalate to prolonged collision. They are high-speed tests of endurance and maneuverability. The resident male demonstrates superior control, often forcing the intruder to retreat without direct contact. Through repeated territorial skirmishes, flight precision sharpens. The wetland itself demands adaptability. Rising thermals create updrafts that can lift a dragonfly unexpectedly, while cooler currents descending from shaded banks require compensatory wing beat changes. By flying repeated loops at varying altitudes, the dragonfly learns the microclimate of his territory. These environmental calibrations enhance future hunting efficiency. When genuine prey appears, he can integrate wind drift into interception calculations without hesitation. Muscle physiology underpins this performance. Dragonflies possess asynchronous flight muscles capable of high-frequency contraction sustained over extended periods. Repeated patrol flights maintain these muscles near peak readiness. Unlike insects that rely on short bursts of flight, dragonflies operate as aerial specialists. Continuous movement prevents stiffness and preserves reaction time. In effect, the air above the pond becomes a training ground where endurance and agility are honed simultaneously. Predator avoidance intertwines with these drills. Swallows and frogs lurk at the margins of the wetland. A dragonfly that misjudges altitude or slows abruptly becomes vulnerable. Practicing rapid vertical climbs and lateral darts enhances escape potential. When a bird swoops, the dragonfly's response appears instantaneous, yet it mirrors maneuvers rehearsed countless times during routine patrol. The violence of predator evasion, like that of prey interception, is embedded within daily flight patterns. Occasionally, the dragonfly hovers motionless above the water, wings vibrating in place. This hover is not rest, but calibration. Subtle wing angle adjustments stabilize position against crosswinds. During such pauses, the dragonfly may pivot slightly, scanning the surface for ripples that indicate emerging insects. Even without immediate prey, he may perform a brief forward surge followed by a tight turn, as if testing acceleration capacity. These micro-drills maintain readiness. Reproductive behavior also benefits from this training. When a receptive female enters the territory, the male must intercept her swiftly, clasping behind the head with specialized abdominal appendages. This maneuver requires precision alignment in flight. Territorial patrol and mock interceptions refine the spatial awareness necessary for successful mating. Thus, daily loops serve multiple adaptive functions. As afternoon heat intensifies, flight paths adjust. The dragonfly may rise higher, exploiting stronger thermals to conserve energy while maintaining vigilance. Later, as light angles soften and air cools, patrol altitude lowers again. Each shift recalibrates muscle output relative to temperature and air density. The dragonfly's body responds fluidly, honed by repetition. When a mosquito finally darts into open air, the dragonfly accelerates with startling directness. There is no visible calculation. He angles slightly ahead of the mosquito's path, meeting it mid-air with legs forming a basket that traps the insect in flight. The capture appears effortless because the underlying sequence has been practiced throughout the day. The interception geometry, wing beat timing, and grip alignment are products of continuous rehearsal. As dusk approaches and the wetland quiets, patrol loops shorten. The dragonfly selects a perch among reeds, wings angled to release residual heat. Even at rest, training has not ceased. The day's flights have reinforced neuromuscular patterns that will carry into tomorrow's patrol. The air has functioned as dojo and laboratory, shaping reflex and endurance through constant movement. In the life of the scarlet dragonfly, violence is not episodic, but embedded within routine. Every loop along the shoreline, every rapid turn and aborted surge, refines the machinery of interception. The wetland sky becomes a disciplined arena, where survival depends on rehearsal as much as instinct. When prey appears or rival intrudes, the body responds with practiced certainty, because the air has already taught its lessons in thousands of silent drills. At the margin of a still pond, where duckweed gathers in loose mosaics and the reflection of overhanging branches trembles in faint distortion, the surface appears solid from a distance. Yet it is neither solid nor stable. It is a thin, elastic boundary between air and water, constantly disturbed by falling debris, surfacing insects, and the invisible pressure of shifting wind. Across this restless membrane, a water strider moves with deliberate control. Its long, dark legs press lightly against the surface, dimpling but never breaking it. Each step generates concentric ripples that radiate outward in overlapping rings. To stand here is to inhabit motion itself. The water strider's ability to remain afloat depends on surface tension and specialized leg adaptations. Microscopic hairs coat each leg, trapping air and repelling water. These hydrophobic structures distribute weight across a broad area, preventing penetration of the surface film. Yet flotation alone is insufficient. The pond's surface behaves like a living drum, transmitting vibrations from every disturbance. A struggling insect creates sharp, irregular waves. A fish rising from below produces low-frequency pulses. Even a falling leaf sends a transient pattern across the membrane. For the water strider, every ripple is information. Movement across this shifting plane resembles practice more than simple travel. The strider pushes backward with its middle legs in short, controlled strokes, gliding forward before adjusting with forelegs that act as rudders. It pivots abruptly, then accelerates in another direction, leaving a wake that intersects older ripples. These maneuvers are not always responses to prey. Often the surface ahead is empty. Yet the insect performs sudden turns and feints as though intercepting invisible targets. Through constant skating and redirection, it maintains neuromuscular coordination tuned to the fluid mechanics of the interface. The pond itself is an unpredictable partner in this training. Wind gusts distort the surface, flattening some waves while amplifying others. Temperature gradients alter water viscosity slightly, influencing ripple propagation. During warmer afternoons, convection currents stir beneath the surface, subtly changing wave patterns. The water strider adapts through repetition. Each glide tests friction and tension. Each pivot recalibrates balance. Because the substrate itself moves, stability must be learned anew each day. Sensory organs along the legs amplify this precision. Mechanoreceptors detect minute deflections in the surface film, translating wave amplitude and frequency into neural signals. By skating through varied ripple fields, the strider refines its ability to discriminate between prey and threat. A drowning mosquito produces high-frequency vibrations with irregular peaks. A predatory fish generates broader, smoother waves rising from below. Through constant exposure to minor disturbances, the insect sharpens pattern recognition. Practice occurs continuously, even when hunger is not pressing. Territorial interactions further contribute to this refinement. Males patrol small patches of surface, intercepting rivals with quick darts and lateral slides. Encounters often involve rapid feints, legs raised slightly, and then lowered without direct contact. The two insects circle, sending overlapping ripples toward each other. These wave signals communicate size and readiness without immediate physical aggression. Through repeated skirmishes, striders learn to interpret subtle variations in ripple intensity, adjusting posture accordingly. The sparring unfolds as much in water as in air, a dialogue written in concentric rings. Reproduction depends on this surface literacy. During mating attempts, males must approach females without triggering escape responses. The slightest misjudged ripple can signal threat. Through daily practice in skating and pivoting, males refine approach speed and angle, minimizing disruptive wave patterns. Females, in turn, evaluate these signals, responding differently to controlled glides versus abrupt lunges. The surface becomes both arena and testing ground for nuanced communication. Predator presence reinforces the importance of rapid response. Fish such as sunfish patrol beneath, using upward strikes to snatch unwary striders. When a large subsurface wave approaches, the strider reacts instantly, pushing off in a direction that minimizes overlap with the incoming ripple. These evasive maneuvers are extensions of daily drills. By performing frequent quick pivots, even in calm conditions, the insect maintains reflex pathways necessary for survival. Prey capture reveals the culmination of this training. When a small insect falls onto the water and begins to struggle, the ripple pattern spreads outward. The strider detects the disturbance and adjusts trajectory mid-glide, aligning with the wave source. It accelerates in short bursts, forelegs reaching forward to grasp the prey while maintaining balance. The attack must be precise. Excessive force could rupture the surface film and sink both predator and prey. The strider's control over leg pressure and body weight reflects constant rehearsal in modulating contact with the membrane. Environmental fluctuations such as rainfall introduce further complexity. After a storm, the pond surface is fragmented by overlapping raindrop impacts. The water strider continues to skate amid this chaos, interpreting meaningful signals within noise. Repeated exposure to such conditions trains discrimination under uncertainty. Minor wave signals become distinguishable even within turbulent backgrounds. Thermoregulation also shapes behavior. As temperatures rise, metabolic rate increases, enabling faster acceleration and more agile turns. During cooler periods, skating becomes more measured, conserving energy while maintaining vigilance. The strider adjusts stroke frequency and glide length according to internal state, refining muscle coordination across thermal gradients. Symbiotic interactions occasionally occur when smaller aquatic insects share the surface. Water striders may ignore harmless species while responding rapidly to potential prey. These selective reactions are honed through experience. The insect learns, at a physiological level, which wave signatures correspond to nutritional opportunity and which signal risk. As evening approaches and light fades, the pond surface smooths. The water strider continues short patrol circuits, creating faint ripples that fade quickly into darkness. Even in reduced activity, minor adjustments persist. A brief pivot here, a controlled glide there. Training does not cease. It integrates seamlessly into routine existence. On water, where the ground is fluid and every step reshapes the substrate, control is survival. The water strider's daily skating and pivoting constitute continuous rehearsal in balance, interpretation, and restraint. Violence, when it occurs, is swift and exact because the body has practiced modulation thousands of times. The pond's surface is both battlefield and classroom, its ripples shaping a predator whose mastery lies in reading motion faster than enemies can generate it.